Next method is Hook and Jeeves method. The pattern search method of Hook and Jeeves is a sequential technique, each step of which consists of two kinds of moves, the exploratory move and the pattern move. The first kind of move is included to explore the local behavior of the objective function. The second kind of move is included to take advantage of the pattern direction. The general procedure can be explained by the following steps. Step 1. Start with an arbitrarily chosen point x1 called the starting base point and the prescribed step length delta xi in each of the coordinate directions ui, I equal to 1, 2, 3, etc. Set k equal to 1. Second step, compute fk, that is f of xk. Set I equal to 1, then yk I minus 1, that's equal to yk naught, yk 0 equal to xk. And start the exploratory move as stated in step 3. Step 3. The variable xi is make unstable about the current temporary base point yk I minus 1 to obtain the new temporary base point as yk I equal to yk I minus 1 plus delta xi ui if f plus equal to f of yk I minus 1 plus delta xi ui, which is less than f, and yki is equal to yki minus 1 minus delta xi ui if f minus, that's equal to f of yki minus 1 minus delta xi ui, which is less than f, which is less than f plus, and yki is equal to yki minus 1 if f equal to, if f is less than minimum of f plus and f minus. This process of finding the new temporary base point is continued for I equal to 1 to etc. until xn is to find ykn. Fourth step is, if the point ykn remains same as xk, reduce step length delta xi, say by a factor of 2. Set I equal to 1 and then go to step 3. If ykn is different from xk, obtain new base point as xk plus 1 equal to ykn and go to step 5. With the help of the base point xk and xk plus 1, establish a pattern direction S as S equal to xk plus 1 minus xk and find a point yk plus 1 0. That is yk plus 1 0 equal to xk plus 1 plus lambda s. Alternatively, we can solve a one-dimensional minimization problem in the direction S and use the optimum step length lambda star in place of lambda in equation 1. Next, step 6 is set k equal to k plus 1 and fk equal to fk, that's equal to f at yk 0, I equal to 1, and repeat step 3. If at the end of step 3 f of ikn is less than f of xk, we take the new base point as xk plus 1 equal to ykn and then go to step 5. On the other hand, if f of ikn is greater than f of xk, set xk plus 1 equal to xk. Reduce the step length delta xi. Set k equal to k plus 1 and then go to step 2. The process is assumed to have converged whenever the step length falls below a small quantity epsilon. Thus, the process terminated if maximum delta xi is less than epsilon. We can summarize the Hook and Jeeves method in the following steps. Start with an arbitrary chosen point x1. We have two unit vectors u1. We can denote u1 or s1 as 1 0, u2 or s2 as 0 1 in x direction, y direction respectively. From the point x1, we can either proceed along positive direction of u1 or along its negative direction, that is along horizontally. Next, we get points on either side of x1 as x1 plus delta x1 u1 and x1 minus delta x1 u1. Find f at x1, that is denote x1 as fy10. Calculate f at y10 as f of Then f of x1 plus delta x1 u1, denote it as f plus, and f of x1 minus delta x1 u1, denote it as f minus. Find minimum among them. Say f of x1 minus delta x1 u1 is minimum. Mark it as y11. Then proceed along negative or positive direction of u2 vertically. So after horizontal move, we have to move vertically. Again we get points on either side of y11. Find f at y11, f at y11 plus delta x2 u2, and f at y11 minus delta x2 u2, and minimum among them, say y11 minus delta x2 u2. Then make it as y12 or x2. Up to step number 8, the moves are called exploratory move. Now identify a pattern direction S equal to x2 minus x1. Locate x3 along direction S such that x3 equal to x2 plus lambda S. To find x3, find lambda value which minimize the function f and make x3 equal to y20. Then calculate del f at x3. Then find the value. If it is equal to 0, that point becomes optimal. Otherwise, repeat the whole process till we reach del f at xj equal to 0. The step 9 to 12, the moves are known as pattern move. So this is summary of Hook and Jeeves method. You can use this summary in doing problems. Now we can see an example. Minimize f of x1 x2 equal to minus x1 minus x2 plus x1 square plus 6x1 x2 plus 3x2 square, starting from the point x1 2 minus 1. Take delta x1 delta x2 equal to 0.5. Perform 2 iterations. We can find the solution. First iteration, take the starting base point as x1 2 minus 1. Step length that is given in the problem as delta x1 delta x2 equal to 0.5 along the coordinate directions u1 and u2. Set k equal to 1. So starting point x1, let us denote by y10 equal to 2 minus 1. Then we can calculate f of x1 equal to, after calculation the value equal to minus 6. Then we will calculate f plus and f minus. F plus equal to f of x1 plus delta x1 u1. x1 delta x1 u1 are all given. So after calculation the value becomes minus 7.25. F minus equal to f of x1 minus delta x1 u1. Then the value is minus 4.25. Then f plus is minimum. So minimum exists at the point 2.5 minus 1. Then let us denote the point as y11 equal to 2.5 minus 1. Then we calculate function at value y11, f at y11 equal to minus 7.25, and f plus and f minus at that point. F plus equal to f of y11 plus delta x2 u2. That is along the y direction, along the vertical direction. That is, after calculation we will get minus 2.5. F minus equal to f of y11 minus delta x2 u2. The value is minus 10.5. Then the minimum is at f minus, that is minimum exists at the point 2.5 minus 1, 2.5 minus 1.5. Then let us denote by y12, that's equal to x2. So we got x1 and x2. Then we can calculate the step length as equal to x2 minus x1, that's equal to 0.5 minus 0.5. So x3 equal to x2 plus lambda s. Then after simplification we will get 2.5 plus 0.5 lambda minus 1.5 minus 0.5 lambda. Then calculate the function at that point x2 plus lambda is. You will get a quadratic equation in lambda. So to find the minimum, find the first derivative df by d lambda, then equate to 0. You will get the lambda value as minus 5, denote it as lambda star. Then we can calculate x3 as x3 equal to x2 plus lambda star s. Then after substitution we will get x3 as 0, 1. Then you calculate del f at x3. Del f at x3 is 0, 1. If that del f value is approximately equal to 0, we can say that that corresponding point is the optimum point. Here it is not approximately not equal to 0. So we have to move to the next iteration. In the second iteration, take y to 0, that is denoted as x3 equal to 0, 1. Then y21 equal to minus 0.51. Calculate the function value at y20, that is f at y20 equal to f plus equal to 4.75, f minus equal to minus 0.25. Then f plus equal to f at y21 plus delta x2u2, and after simplification value becomes 1.5. f minus equal to f of y21 minus delta x2u2. Then after simplification the answer is minus 0.5. The second iteration, we will get y20 equal to x3, that's equal to 0, 1, y21 equal to minus 0.51. Then we can calculate function value at y20, that's equal to f plus f minus values are given us. After calculation we will get at 4.75 minus 0.25. Then f plus equal to f of y21 plus delta x2u2 in vertical direction. So answer is 1.5. F minus f of y21 minus delta x2u2, that's equal to minus 0.5. So we got the point x4 as denoted as y22 equal to minus 0.5, 0.5. So s step length s equal to x4 minus x3, that equal to minus 0.5, minus 0.5. x5 equal to x4 plus lambda s. Substitute this value in the function. So you will get a quadratic equation in lambda, that's equal to lambda square minus lambda minus 1. Then to find the minimum, find the derivative, equal to 0, we will get lambda denoted as lambda star equal to 0.25. So xy equal to x4 plus lambda star s, that's equal to minus 0.625.375. Then calculate del f at that x5, that is equal to 0, 2.5. So it is approximately, okay, that is approaching the value, del f value approaching to 0, 0. So we can stop the procedure since it was given in the problem only 2 iterations. That means we can stop the procedure, and the minimum exists at the point x5, that is equal to minus 0.625, 0.375.